Okay, review for test 2 for Physics 214, which is tomorrow. Usual fare, 10 to noon. Nothing afterwards, no lab, no nothing. From what I understand, the TAs will be tutoring somewhere. We got a conference next door. The old tutoring room is taken. Where these tutors are planning on working, I don't know. Yes.
I have a quick question.
Yes.
So on the test that you did on Friday,
Mm-hmm.
the Faraday's law problem 2, you just found the time and you used -2 Tesla. Why did you use -2?
Because I knew that the change in the B field was into the page. So what? Yeah. Well, the way that the currents are set up, it's a counterclockwise current. And this is the thing about 214 test 2. It's either an up or down. It's a 50-50 shot. So if you don't know what you're doing, it could end up making in trouble. This is the induced current, which means that the induced flux has to be out of the page. It has to be. And that's because Snell's law demands that it has to be opposite of this. So because they're opposite, the only thing that can produce a change in magnetic flux with a fixed area is a changing B field, which means that dB dt has to be in the page as well. And if that dB dt is into the page, for the equation B equals B naught plus dB dt t, that value there is negative. So what you do is you find the magnitude, and then according to the arrangement of the currents and the fluxes and all that stuff, that determines the sign of that value. When you're working, in just a second, when you're working with EMF d phi b dt, A dB dt, and I, which is that, I deal with magnitudes in this particular case. It's not going to affect anything. What will affect things is if you use the wrong sign right here. So this is critical to use the right sign. And so, and these, anything out is positive, anything in is negative. So if I say that the final B field is 2 Tesla into the page, numerically in this equation it would have -2. If it was half a Tesla out of the page, it would be positive half. Your question.
Once you determine which way the external force or the external...
How did I determine?
Or once you determine that, is it always parallel to dB dt? The external?
The external dB dt will always be parallel to, oops, that's the wrong symbol. It will always be parallel to d phi b dt. Some people just write it like that. But the anti-parallel are those two, that the d phi b dt is anti-parallel to phi b induced. In this particular case, the case with the circle and the changing B field, yes, the dB dt is always in the same direction as the d phi b dt. Now with the moving bar, things get weird. It depends mainly on, is the area getting bigger or smaller. I think if it's getting bigger, they're parallel. If it's getting smaller, they're anti-parallel. Wow. Next question. Okay. Someone has asked over the weekend to work through, and I said, yeah, that's what we're planning on doing anyway, is the sample test 2. The just general outline before we really get kicked into it. 25 multiple choice. I'm taking out like the vector addition stuff and all that stuff. The ones that you really need to pay attention. Oh, and obviously none of that ideal or non-ideal voltmeter, ammeter stuff. We tested that on test 1. But the forces on a wire, definitely motions causing delta V across circuits, because you have to know that for Kirchhoff's law. The other one that we need to do is B fields. You have a wire, the current is going floor to ceiling. In which direction is the B field? It's coming at you and then away from you on the right, and understanding, and at a point which is at you, it's going from left to right. Because if we look at this is from the top view. The B field at that point is going like that. The B field there is going like that, which means in front of you, it's going like that, because the B field, that's a horrible circle, but it kind of looks like that. So know all of these. There's a few others, but the big stuff, like I won't ask about RC circuits. It'll be focused on magnetic fields, magnetic flux, Faraday's law, Lenz's law, force on a wire, maybe a few of the units of flux, units of B field, all that stuff. Stuff like that. All right. This is a sample from an old test. I've forgotten where it came from. I think I may have just pulled it out of someplace else. We won't do matching, or I call it multiple selection. We've done right-hand rule enough. It won't be like this. It will be like that, where there'll be a missing, either the first vector or the second vector will be missing. I may get creative and one of the vectors will be the third vector, but it'll be something like this. So as in this example, A is the vertical, D is the horizontal. The answer can either be either E or F. So if you do out of the page towards A, you get D, which is where the thumb points. So it has to be E, like that. So stuff like this. None of this negative sign garbage. We're not playing that. Okay, Kirchhoff's law. Just as I'm thinking about it, we will not do RC circuits. It'll be vector field addition. This was back in the old days where I think we took a little bit too much time in test 1 material. So in Kirchhoff's law, all we got to do is set this dude up. You have 2 loops that will represent the 2 currents, J1 and J2, We all go clockwise. We all follow the number line current J2 and J1. So in this particular case, we go plus to minus, minus V1. The battery on the left I declare as V1. Minus J1R1, which is the 10 ohms. Let me label them real quick. V1, R1, R2, and R3, and V2. Minus J1 R2 plus J2 R2. And that is all equal to 0. So that's a full loop. Remember that when you go through the middle resistor, it's all direction dependent. If you go from top to bottom, you're going with J1 but against J2. If you're going from bottom to top, you're going with J2 but against J1. Factor out common. You get this, plug in the values, minus 20. Oop, the sign is there, or the parentheses. J1, R1 plus R2 is 30. Not very creative selection on resistors. Plus 20 J2. Everything is a factor of 10, so minus 2 minus 3J1 plus 2J2. And that's the first circuit. We could solve for J2. J2 is equal to 3J1 plus 2, and then J2 is equal to 3J1 plus 2 over 2. Now for loop 2. Loop 2 starts bottom left, goes with J2 across R2, but against J1. I go with J2 across R3, and then I go from negative to positive, so positive V2. And that gives me this. Just looking at the resistors and the batteries, my prediction is that J1 will be negative and J2 will be positive. So we get minus J2 R2 plus R3 minus J2. Nope. That goes in this. This is J1 R2, and it's positive. Plus V2 equals 0. Next. Plug in values. Minus J2, R2 and R3 gives you 30. J1 and R2 give you 20, or I'm sorry, just R2. 20 J1, and then V2 is 15 volts. Everything has a common multiple of 5, so it's minus 6 J2 plus 4 J1 plus 3. 0. Now J2 is equal to this, so it's minus 6, 3J2 plus 2 over 2.
3J1.
Oh, 3J1, thank you. Yes, I was bringing that down, and this is a substitution. 4J1 plus 3 equals 0. This gives me negative 3 times 3 is negative 9. J1, negative 3 times 2 is negative 6. No J's. Plus 4J1 plus 3 is equal to 0. This gives you minus 5J1 minus 3 is equal to 0. So negative 5J1 is equal to 3, or J1 is equal to negative 3/5 amp. So J1 is negative, which we pretty much knew from the beginning, but sometimes it gets weird. J2 is equal to 3J1 plus 2 is 2. This becomes minus 3/5 times 3 plus 2 divided by 2. So this is minus 9/5. This is 10/5. This leaves me with 1/5 over 2, which is equal to 1/10 amp. And it is positive. So you end up with a negative J1, which means that the current I is going counterclockwise with the magnitude of 0.6. I really got the numbers to work out well. This one is a positive 1/10, which means the current runs clockwise with the magnitude of 1/10 amp. When you're looking at the middle resistor, I1 is coming down the bottom and going up. I2 is coming down the bottom and going up. So both of them are going in the same direction. So I in the middle is 0.6 plus 0.1, or 0.7 amps. And so that's the answer for the Kirchhoff's law. Now there is, I doubt it will happen. I try not to make it happen, but it's happened twice, once in a final and once in a test last year. The final had happened like 3 years ago. The test had happened last semester. I ended up with the test on the, Kirchhoff's law on the problem where I got I1 is equal to 1/2 amp and I2 is equal to 1/2 amp. And people lost their ever-loving minds, just went insane. So I1 is clockwise with the magnitude of 1/2. I2 is clockwise again with the magnitude of 1/2, which means that you've got 0.5 coming down and 0.5 coming up. What is the total current through the resistor? 0. That's the answer. It happened, I've never given one on a problem set. It's happened twice in the 7 years that I've been teaching. But that's how you do it. That's how you handle it. I had a person snap in the middle of the final because it ended up being 0. Just lost her mind. I'm like, 0 sometimes is an answer. It's not that bad. Yes.
So, even though like I1 is going counterclockwise and I2 is going clockwise, since they're both pointing, like both of the arrows are pointing up, that's why they're both positive.
Yes. All you're caring about are the directions of the current from the frame of reference of that middle resistor. If I just said this is R2 and you had one current I1 like this and the other current I2 like that, what's the total current through the resistor? It's a sum. So what you have to do is you have to know that this is a focused part of that. And that this is a focused part of that. In this case, it is negative or counterclockwise. In this, it's positive or clockwise. So you have to kind of like, I mean, this is just pen and paper, but if this was like a big iPad, I would take that and I would finger out and I would blow that thing up, and you could see that from the local perspective, if you're ignoring all of that, you can look at it simply. And that's really how it is. Okay. So once again, problem 3, RC circuits. Don't worry, it's not going to be on the test. Oh. 6 will not be on the test. Let me get rid of the ones. Okay, let's do 4 and 5. Yes.
Whenever you're doing this problem,
Mhm.
does it matter like where you start walking?
It does not matter where you start, just as if when you walk around the room, it doesn't matter which corner. What is important, critical, is that the point that you start is the point where you end. Because what is the change in potential from beginning to end? It's 0. If you start and end at a different location, you won't get that. The starting position doesn't matter. I just do it because I don't want to take the time to go, well, maybe the upper left or the upper right or the lower right. No, I just go lower left and keep going because it really doesn't matter and it's just less thought.
So whenever you do it, could you go like up, forward this way? Like, does it matter?
I would always go clockwise because in the way, now granted, now we're starting to veer off into there are other ways to do it, and I have no problem with those other ways. But the thing is, if you always go clockwise, if your loops are always clockwise, if you stick with this path, you don't end up in the Velociraptor pit. What you're talking about are permutations. Permutations I respect, but I can't control it. And it's just for first year students, this is just the best way to handle it in my opinion. So if during the test you come back and you're missing a face because the Velociraptor got you, I know what you've been doing. So. All right, problem 4. Where is the B field in the B field wires 0? What is the B field at the point A? Where between the two wires is the B field 0? What is the B field at point A? Okay. So the two wires, blue wire and red wire, their currents are in the same direction. Lower wire I'm going to call I2, 0.35 amp. Anything above the wire is out. Anything below the wire is in. And since I don't care about the direction or the B fields above the blue wire, I'm going to ignore that altogether. The blue is 0.2 amps. Anything above the wire again is out. Anything below the wire is in. So the first thing I do is mark all my B fields in the locations where I'm studying. Now, just for thoroughness, the B fields in region 1 and 3 B field will never be 0. Well, technically the snarky answer is the B field will be 0 at infinity, but we're not dealing with infinity. So technically the B field is non-zero in regions 1 and 3 in the way that this is set up, so we don't even bother looking for 0 in those regions. The 0 one is in here. What we're going to do is I'm going to set, we could pick, it really doesn't matter. I'm going to pick that region as X. This was given to us as L, which means that that distance there is L minus X. So the first part is find where it's 0. The sum of the B fields is 0, which is equal to B from 1. And actually what I'm going to do is on the next line. B field generic on a wire is mu naught I over 2 pi r. B1 is negative, so it's going to be negative mu naught I over 2 pi r. And this is I1 over R1. B2 is positive mu naught I2 over 2 pi R2. Mu naught I1 over 2 pi R1 equals mu naught I2 over 2 pi R2. Yes?
How is B1 negative, or B1 plus B2 negative?
Well, this is just generic B, or these are the value B1, which would be some negative number. The negative symbol hasn't popped out yet. Will it make you feel comfortable if I just do that? Either way is okay.
Why is it negative?
Well, it's negative because it's going into the page. When you look at this, the blue is in and the red is out, which means technically this is right without the minus signs, but I say B1 is negative mu naught I over 2 pi R1.
Why is it B2 negative?
Because the red is out of the page. The point that we're studying here, because if we read the question, where between the two wires is the B field 0, question mark, that's the first problem. So it has to be in a position somewhere in the middle. The preface of the whole thing was me excluding 1 and 3. So it has to be here. It's below the blue wire, so that B field is in, which will make that negative. It's above the red line, which means this is positive. And that lets you know what the signs are. So it's I1. Now R1 is X. I2 is L minus X. Solve for X. Interesting. All right. Cross multiply. And I'm looking for X. Ooh, what did I do? I messed this up. This is I2, because the X gets kicked out. All right, let's look at the algebra again. Distribute the I1. That comes down. Move that over there. That becomes positive. That comes down. That comes down. X gets factored out. I2 plus I1. That goes down. That comes down under this, the I2 plus I1, to get me this. The units check out. Current divided by current is nothing. I'm left with a distance, and that is equal to X. I1.2 L. It's at 5 millimeters. The units probably, it won't matter. I2.35 plus 0.2. I'm keeping the millimeters because probably I wanted the answer in millimeters. It doesn't make, you could switch it to meters, but it won't make any difference because it's, those amps cancel with that amp, and then you're left with whatever unit you have. So 0.2 times 5 divided by 0.55. And so this is 1.81 millimeters below I1. Because I set my X to be the distance from the upper wire. Next, give me the point, what is the value of the B field at point A? So for point A, which is down here, that distance there, I'm gonna call Y. Why not? It's still double negative. Or no, it's not still. It is double negative. I1's going to be negative. I2's going to be negative. We're going to have a negative B field, so it better be negative. The way that the B fields add up is B1 plus B2. B1 is minus mu naught I1 over 2 pi R1 minus mu naught I2 over 2 pi R2 which leaves me with minus mu naught over 2 pi I1 over R1 plus I2 over R2. Now, R1 and R2 are the distances from the wire to the point. In wire 1, it is L plus Y. You've got to go the distance L, which is the distance between the two wires, and then you've got to go a distance Y. Then I2 is then simply Y, that distance. Now in this particular case, we are going to have to convert the units to meters because when you're calculating the B field, all of the units must be standard units. The mu naught is 4 pi times 10 to the negative 7 over 2 pi. There are meters all throughout that constant. I1, this has to be in amps, 0.2. And now that I'm thinking about it, you could even use milliamps in here because milliamps divided by milliamps still cancels. It doesn't really matter. Big L, 0.005 plus 0.003. So everything here now has to be in meters. Plus 0.35 divided by 0.003. this has possibilities of working out. Awesome. That cancels with that to get 2. Oh, the numbers didn't work out perfectly. 2.83 times 10 to the negative 5 Tesla.
You forgot a minus sign.
Did I? Where? Oh, big deal. Minus, minus. There you go. Because how I would immediately start looking at it and going, didn't I just say it was negative? And then, so fine, I forgot a negative sign. If I was grading, I'd only take off 2, 3 points. With this current grader, I don't know, 12 out of 15, I guess. So, and like I've said before, there's gonna be at least a 5-point correction on test 1. It feels comfortable. I feel comfortable with that. Unless you guys start just well, let's just make it at minimum 5. I'm holding the floor at 5 points. It could go up higher if I need more, but 5 is the minimum. Yes?
This may be like a dumb question.
Mm-hmm.
But, so when the wire's going, like, the current's going this way.
Yeah.
You do the right angle like this is like out of the page, this is into the page. But when
You just did the same hand motion for in and out. So if we had, hold on, I need, doing hand gestures from 20 feet away is different. Yes, I'm coming toward you. So you said what is what?
Like with the current, like the problem we just did, and you're sitting, you put your hand like this, right?
Yeah. Let's say the imaginary wall is here, and the current is like going this way. So it's coming out of the imaginary wall, above the wall.
Just holding your hand like this. Or not like this.
Right now, okay, now I see what your problem is. You're looking at the page. Hold the page up like this wall.
Like this.
Now,
Like this.
see, follow her now. So if you put the thumb like this, the fingers are physically coming out of the paper. Exactly. See?
Okay.
If I wasn't here, you could teach the class. So the thumb is going with the current, which is, according to your piece of paper, is to the right. So when you curve your fingers out, it's coming out of the page.
Oh.
And then when you continue around, it goes into the page.
And then with the current was going this way, it's going into the page and then it goes, okay.
Excellent. See that? And from what I understand, the rates are reasonable for tutoring. So, yes.
Okay, mine's about the right angle too.
Yes.
So I understand how to figure out like what's positive or what's negative for finding a B field, but when it comes to finding X, I don't.
Comes to finding X. Well, what's
Yes.
X?
So finding 0.
Oh, for finding the point at the 0. The right now these are 2 wires where the current is coming straight at you. In fact, the left one I'm gonna make red and the right one is blue. To get the B field direction, put your thumb in the direction of the current, which is directly out of the page, and then the current wraps around it. So the B field from red at that point is this, that, and that. For the blue field, it again wraps counterclockwise. So it is like this, that. Now I'm looking at this from dead on. This and that. So at this particular point, those 2 B fields are opposing each other. This is R2, and that is R1 for I1. So when I said find the point at which at the B field is 0, what I'm really saying is that those two B fields cancel so that the sum is 0. You got an up, you got a down, they add up to be 0. And that's what I'm asking for. Now what, you said find X.
No, I can't like figure out which B is positive or negative when you're
If it's
trying
physically,
to find
well,
X.
what the big deal is, as long as they're both going in the same direction, they'll just add up and the magnitude gets bigger. If they're opposing each other like this, it doesn't really matter if the outward vector is positive. What is important is that they're always opposite. So it's if you get into a quandary of, well, which sign should be negative, all there needs to be is just one, if the B fields are opposing each other. Now the B field is negative if it's going into the page. With B field addition, sign is important. In a lot of other cases, I just don't care. It's magnitude and let reason work it out. So, does that answer the question? Okay, she's busy having a conversation. Just sit here. Does that answer? I think it does, since you're obviously moving on to something else.
It's not like all that. It's so I understand if you go this way for the current and then you wrap.
Yeah.
And you point your thumb out, and that's positive or negative B field.
You've just used both right-hand rules at the same time, which is and this is a problem that I've seen before. If the question is, given a current, what is its B field? You use the wrap rule to determine signs. That's where thumb is I and finger wrap is B. For forces on a charge or a wire in a pre-existing or we could think of it as like external B field. Then we use the F equals ILB or F equals QVB. And for these, how I tend to think of it as, if I just want direction, LI, doesn't really matter, I cross B. For these use, that is the classic right-hand rule. This one is a wrap rule. I don't even think of it as, it's not a right-hand rule. It is just some little shortcut. It's because that, I mean, we just don't have the time or the sanity to deal with the Biot-Savart law, which I mean, there's no need to learn it when all you got to do is this wrap rule. It's two different hand gestures for two different situations. If you want to know what the B field is because of the current, wrap rule. To understand what effect a B field has on a charge or a wire, you use the right hand rule. And they're two different things. Does that answer?
Yes.
I think that's what, because the problem that you have, I've dealt with it before. Now that I've diagnosed what you're thinking, now I can fix it. It's two different situations.
Okay.
You've got to be prepared to identify the correct situation. And now I'm trying to think of design a problem just for you tomorrow. Well, I'm going to give it to the class, but it'll just be for you. Find your weaknesses and expose them. Oh, it'll be fun. So what else about this problem? It's a good discussion. Now, problem 4 uses the wrap rule. Problem 5 uses the right hand rule. Problem 5 is a charged particle with a velocity of 1200, it has to be meters per second, comes in, it's a helium nucleus, so its charge is 2 times 1.6 times 10 to the negative 19 coulombs. It's a helium nucleus, which means we're just dealing with 2 protons and 2 neutrons. I think, did I give, no, I didn't give them. The mass, since it is a helium nucleus, and don't worry, on the test, I'll give you the mass. I'm not into this gunk anymore with proton and neutron mass, as far as I'm concerned, are 1.67 times 10 to the negative 27. So it's 4 times 1.67 times 10 to the negative 27 kilograms. There is a slight difference, but 1 part in 1600, or almost 1700, I don't give a flip about. It enters a magnetic field. This is a positive charge. It banks left. And it lands at a particular distance of, we'll call it D, which is 2 meters. What I want to know is, what is the B field magnitude and in which direction is the B field? Since it is a positive particle and we're using V cross B, I don't have to worry about flipping the sign because it's a positive charge. So V, to get my thumb to shift left, the B field must be into the page in order for the magnetic force to be left. So V cross B, magnetic force to the left, so that's why it'll bank left. If it was a negative particle, if that was a negative particle and it still banked left, the B field would be out because V cross B would be in this direction. It's a negative charge, so you flip. But this is positive, so you have to go V, B there. In problem 4, you were looking for the B field and in which direction. In problem 5, I give you the B field and I tell you it's either going in or out. Figure out which way it is and then figure out the magnitude. It's not produced by a wire. This B field is not produced by a wire. It's produced by like a big rebellion magnet or whatever that I say it creates a field of that strength. So it banks left. it's a circular motion situation. So the sum of the forces radially, which is MA, is equal to mv squared over r. There's only one force acting on this, QVB. One of the V's cancels. And now's the question, like, what am I looking for? Magnitude of B field. So this is MV over RQ. That's a bad looking Q. Is B, so M is 4 times 1.67 times 10 to the negative 27. Velocity is 1200. R is, now this is the question, a lot of people make this mistake. If that distance is 2, what's R? 1. It's just half the distance because it's a semicircle. So that becomes 1. The Q is 2 times 1.6 times 10 to the negative 19. Oh, if that was only 1.67, I'd be very happy. That I'm not willing to round. So I get 2.505, 2.5 times 10 to the negative 5 Tesla. Close enough. And it is, if we're really going to go with a value, I would accept 2.5 times 10 to the negative 5 into page. Because I specifically say magnitude and direction. In the old days, I just said, well, what's the B field? And everyone were all freaking out. Should I put a positive or a negative? Should I say into, out of? This is why I say magnitude and direction. All right, problem 6, we skip. Next problem, or test. Oh, wow. Ooh, all right. This is, when did I start teaching? This must be my second 214 for the spring. We can see how the test has evolved. No version number, very simple rules, all that stuff. Same format as the other one. The multiple selection won't be there, right-hand rule, the difference we've explained before. We're gonna skip Kirchhoff's laws due to time restraints, and we've already covered it so many times. Problem 4, lost magnetic fields. 2 wires of infinite length carry currents as labeled. Dr. Eschenberg has hidden a point or 2 points or 3 points. He's tired and forgotten where the B field is 0. Where is R, the B field 0? This is exactly like the problem that I talked with you guys last week. I think this was the one where there were the 4 groups of students, the 3 main groups and the other group which were split in half. When you look at this, this is the blue current. That is the red current. Now we're looking for the magnetic field that's created, not the effects from the magnetic field. So in this particular case, we are going to use the wrap rule. B field for blue, into the page above, out of the page below. Now, red, out of the page above, into the page below. it is impossible for the B field to be 0 in this region because it's positive, positive. Yes?
Why is the red end of the page above?
Oh, I'm sorry. That fixes. Anything above the red wire. It can't go above, out of above and into above. That would be contradictory. So thank you. So it goes out and then in. The middle region is impossible. The upper region is impossible as well. And I've talked about it in lecture. I'll talk about it briefly now. If you are at a point here, the B field from 1 will always be greater than the B field from 2 in terms of their magnitudes. And why is that? This one is a very strong current compared to the weak one, which means at a particular point out here, this point, regardless of where you are above wire 1, B1 will always be, or this point will always be closer to wire 1, which is stronger in current, than the one that's further away with the weaker current. So the B field contribution from B2 will always be less than the B contribution from region 1. It's numerically impossible. If you set it up, if you set this X to be that point, you'll end up with an X that ends up being negative, which basically lets you know that you were looking in the wrong direction. And this example was done in class. The distance that we are looking for has to be down here, negative, positive. So I'm going to call that distance X. The sum of the B fields is equal to 0, which is B from 1 and B2. B1 is positive mu naught I over 2 pi r minus mu naught I2 over 2 pi r2. Now at this point, to address once again one of your problems, if you couldn't remember if is in or out, there's in positive or out positive. I always get them confused. It doesn't really matter as long as those signs are opposite, because what you're going to do is you're going to bring over the other one anyway, and it all works out. And I made a whoopsie. There we go. So those cancel. Now, R2 is the distance from R2, or from wire 2 to the point, so it's X. Wire 1 current is I1. Its distance is X plus, and it would probably help if I gave you the distance between the two, which means that this wasn't probably correct. So we'll go 0.1 meters. Totally valid question to ask during the test. And I'm going to say that that is L. All right, next, solve for X. Get your X's on one side. I'm going to divide everything by -1. That's a big X. Factor out the X. And you get that. So I2 is 80 milliamps. L is 0.1 meter. I1 is 600 milliamps. I2 is 80. I keep them in milliamps because it doesn't matter if you convert them to amps or milliamps. They're still going to cancel out, including the conversion, so there's no real point in doing this. If I wanted the answer in meters, use 0.1. If I wanted the answer in millimeters, I would have used 100. And I get an answer of 0.0154 meters, or 15.4 millimeters is the answer that I would give. And that is 1.0154 meters below I2. Had I originally looked in the distance of the distance above I1, I would have ended up with a negative number of 0.1154. If you're searching above like that, the upper wire, you would end up with a negative number, which would then put you right back into the same location. So that's number 4. So it's creeped up a lot. Also, back in the old days, what was really interesting is that the way that the tests were set up, we had one 25-point matching or selection, multiple selection part, and then 3 big 25-point problems. Now we've shifted into multiple choice, where the problems may be a little bit smaller, but they're worth less, and then we got a big hunk of multiple choice. Tail of 3 particles. This is the last one that we got. 3 particles enter a B field, one after another as shown. They have the following properties. I give you the mass, I give you the charge, I give you the velocity of each. The blue particle lands right four meters to the right of where it entered. What is the magnitude of the B field? So for this, first thing I'd like to do is figure out the magnitude. The charge of blue is positive, 1 times 10 to the negative 6. So to get the force vector to go to the right for a positive charge, V is in this direction, B is out of the page, so that the force vector is my thumb. So the B field has to be out. It has to be out of the page. Now let's determine magnitude. For the positive particle, the sum of the forces, which is ma, is equal to mv squared over r. The only force that we have is the magnetic force on a particle, QVB. I'm looking for B, so mv over rq is equal to B. The m is 1 times 1 to the negative 10, or 1 times 10 to the negative 10. V is 1.2 kilometers per second, or 1,200 meters per second. R is 2. And then Q is 1 times 10 to the negative 6. So the B field is 0.06 Tesla. That's the B field out of the page. That gives me the magnitude, and then logic gave me the direction. Now I have a negative particle, the red particle, and I'm looking for its distance at which it lands. Where does the red and green particles land? So once again, I have this, mv squared over r is equal to qvb. But now I'm looking for r. mv over qb is equal to r, or 2mv over qb is equal to d. 2 times 3 times 10 to the negative 10. The V is 3,600. The charge is 0.5 times 10 to the negative 6. I'm dealing with only magnitudes because I know where this thing's going to land. It's going to land to the left. And my B is 0.06.
Is it 2 times because you're trying to get the diameter?
Yes. The equations produce the radius, but the answer says how far away did it land, which means 2 times r, or diameter.
Why don't you use negative for the charge and the?
Because I'm only dealing with magnitudes. Because, I mean, the negative sign doesn't do anything for me. It doesn't, like I said before, negative signs are shifty. They can't be trusted. So keep your, I use direction with logic, and then magnitudes of everything to get the magnitude. Unless I'm adding vectors, then you gotta have signs running around. Oh man, you made me clear the problem out of my calculator. So this is 6. And I get a distance of, wow, hold on. And yeah, I can tell because it's 3 times as fast. I get 180 meters. Okay, fine, you're dealing with 100, but the number's exact. Now, particle green, it's neutral. Where does it land, to the left or right? It doesn't land. The magnetic force as a vector is Q V cross B. Yes, V cross B is a vector. It will produce a vector. V, B, V cross B is to the right. But the charge of a neutron, or a neutral particle, is 0. 0 times right is nothing. So that one will not land. And that's the answer. That also freaked kids out. They were like, but it doesn't land. Well, that's the answer. Sometimes the answer is, I don't know. Sometimes the answer is, it doesn't land. And then that's it from test 2. So the big guns, Kirchhoff's law, and magnetic induction. The wild card will be either, I mean, we pretty much know how it is. B field addition, force on a wire, force on a particle. This I like. This is particle spectroscopy. I may add a velocity selector to it as well. And we did that at the end of the lecture on Friday. Stuff like, I mean, yeah, I outlined it. Stuff like this I love. The B fields all adding up. The one on the problem set, I mean, it could get weird. So know how to do problem set 4, number 4. How to add up B field magnitudes and stuff like that. We talked about it. We talked about the specific problems from all the problem sets before in that Friday lecture. If we can kill time until 11:30, then I'd be happy.
Can you do number 5 on problem set 6?
Problem 5 on problem set 6. Problem 5 on number set 6. Oh. This is exactly like this problem here.
Is it the torque bar one? That's the one I mean.
Oh, well, had you said problem 4 on problem set 6. And that'd be it. Because we just did number 5 effectively. All right, number 4. 4, actually, yeah, I kind of like it. I like it. It's a cute little problem. It is a hybrid problem. All of you supposedly have taken a 213 class from somebody. It is a combination of torque bar, and force on a wire hybrid problem. You know what I'm talking about. All right. So to draw this thing out, we have the force of gravity from M on that side. The mass of the bar does exist. It is at a half point, its center of mass of the bar. The bar has a uniform mass density, which, oh my goodness, that would just mess things up to no end if it had an ununiform mass density. Which means that if it's at the midpoint, that distance is 1 meter. And if that distance is 1 meter and that distance is 1 meter, granted, this is not to scale, that distance there is 0.6. That is its distance there. The other thing that we have is the force on a wire. And the current is to the right. The B field is into the page, which means that there is a magnetic force up. And what I did is I simplified it with a force that is centralized at the midpoint of center of mass. It's the center of length. Oh, that would be... No, let's not get into it. So the magnetic force is at the center, the geometric center of the bar. Center of mass is at the geometric center of the bar. Both the magnetic force and the gravity force are in opposite directions, but physically located 0.6 meters to the right of that fulcrum. I have the B field. The big question is, well, what's I? Well, let me simplify this and clear up the sketch. The bar continues on, but in terms of the fulcrums, or I'm sorry, the lever arms, that distance is X. This distance is, I don't know. We'll call it Y. Why not? 0.6 meters. You have a magnetic force of ILB magnitudes, but this is a force with magnitude ILB that is physically located up and to the right of the fulcrum. And then you have force of the bar, which is the mass of the bar times gravity. And that is the simplified version. It's not rotating, so that you know the sum of the torques is equal to 0. Torque is lever arm vector crossed with force vector. Not force cross F. We have distance X times its force mg. We've got FB, which is ILB, times its distance y. And then we have M bar G times its distance y again. So torque is effectively, in magnitude, force times distance. Distance, force. Force, distance. Force, distance. Now I need minus signs and pluses. Always start at the fulcrum and go out to the force. First force, to the left, down, out, positive. That force there, to the right, up, out, positive. Right, down, into the page, or negative. And we get this. But all we got to do now is solve for I. So M bar GY minus XMG is equal to ILBY. G, mass of the bar, Y, minus the mass that's hanging, X, all divided by LBY is equal to I. I have no idea if the numbers are going to make sense. Mass of the bar is 2. Stop it. My calculator is doing something funky. Oh, where were I? 2 times y 0.6 minus 0.2 times 0.4 times 10 divided by oh, and then what's L? Total length of the bar. I was like, we didn't have to know it. We had to know it for force on a wire. 2 times B 2 times Y, which is 0.6. And the current, 4.67 amps. What does that answer that I get? So it's a combination of a torque bar problem combined with force on a wire.
Will there be any hybrids on the test?
Not feeling it. I'm not feeling, because because if the answer now, if I say no on hybrids, then that automatically restricts us from using it automatically puts number 7 off the list of accepted problems. You guys have enough to deal with than try to remember stuff from some first semester. So I would say no. Also, it's because it's technically an hour 15-minute test with Kirchhoff's law, 25 multiple choice, a weird right-hand rule game, the magnetic induction. That's enough abuse already. Magnetic field or force on a wire by itself will be more than enough to do it. The final, still probably not, because there's so much material that we have to cover during the final. So I would say if it's going to be a hybrid, hybrids would show up on the final, but only take into account test 1, 2, and 3 material. Now granted, technically we covered vector addition in 213, but it's vector addition. It's hardcore. We got to know it. All right, 7 minutes. But if we want to go until 1 o'clock, yes.
What's the difference between a velocity selector and a particles?
The question is, it's a very good question. A velocity selector will allow charged particles of the same velocity to pass. Hence, velocity selector. It selects the specific velocities. In the way that this is set up, you've got a uniform E field in one particular direction. Positive particles will feel forces in the direction of the E field. Negative forces or negative particles will feel forces in the opposite direction. Now I'm drawing these two particles separately from each other. They're not, in my world, they're not interfering with each other. And then, so they both have velocities in a particular direction. With a velocity selector, the way that I have to do this is that the B field that is set up must be into the page. Because for a positive particle, V cross B means that the magnetic force is into the, or to the left. For a negative particle, v cross b is to the left, but a negative particle means that it's to the right. So with a correct selection of E fields and B fields, you can tune it such that the sum of the forces in X are equal to 0. If the forces in X are equal to 0, the particle is not going to slam up to the left or to the right. For the positive particle, the magnetic force is negative, QVB. To the right is the electric force, QE. So QVB is equal to QE, or V is E field over B. So from a unit perspective, if you take the electric field, divide it by magnetic field, you get the velocity. Only particles of that velocity will pass through. If it's traveling too fast, the magnetic force is greater than the electric force, and then the positive particle would hit left. If it travels too slow, the magnetic force is less than the electric force. And then in this case, the positive particle would slam up against that wall. So in the end, particles of only a specific velocity could pass through. The velocity selector is so important because what it does is it sifts through all the gunky particles. Say you have a stream of particles where ideally they're traveling at 500 meters per second. But some travel at 509, other travels at 485, and you want to get rid of that gunk. Why is that? Because you want to know what the velocity is specifically, make it a known quantity. Because what you do is you fire positive and negative particles in a particle spectrometer. And it has a B field which is in a very specific direction. It can, in this case, R's are set either into or out of. So let's set our B field to be out of the page. So from a positive particle's perspective, V is this way, B is up. So the magnetic force is to the right, and what will happen is it will begin to go in a circular path and then land a specific distance away, which is 2 times R. For a negative particle, V cross B is to the right, just like V cross B is to the right for the positive particle, but it's a negative charge. So its F cross B is to the left, and what happens is that it goes to the left. You get a D, which is equal to 2R. So a velocity selector sifts out particles to only a specific velocity. If it's too slow or too fast, it doesn't want it. And they just go splotching up against the side. It's a lot like, I think how it works is you want to know a chemical spectrum. of like, what is this gunk made out of? So what you do is you just turn it into a gas, you accelerate the particles up to a specific velocity, but like all experiments, some are a little too slow or a little too fast, and then you send them through, and then when they come out, they go to the left or go to the right, and what ends up happening is that you end up with, depending on the number of particles that come out, you can say, oh, it's made of this material or it's this element or something like that. Because the heavier the particle, the further away it's going to get. So the more massive particles will have a further distance than the lighter particles, which will land closer to it. Now granted, you got to ionize this stuff because atoms are inherently neutral if they have equal number of electrons, protons. But that's great question. Good question to kill some time. All right, any other questions? Some people look like they want to leave right now, which is fine. All right, motions proposed to end the class. Do we have a second? All right, does anyone disagree? All right, I go by, what is it, the Robert's Rules of Orders. If no one disagrees, the motion carries. Bye. See you tomorrow.